The map that should have worked. I want you to picture the Milky Way like a leaf on a slow, deep river, not a calm lake, a current. Our whole local group is drifting through a region called Laniakea, and the speed is not small, about 600 kilometers per second relative to the cosmic microwave background. You feel nothing, but space feels it. So what is Laniakea? Think of a basin. Draw a million tiny arrows showing how galaxies move when you average out their local jostling. Those arrows trace flow lines. Where the arrows converge, you get the center of a gravitational basin. Where they diverge, you hit a ridge or a boundary. Laniakea is that basin on the order of 500 million light-years wide. The map that should have worked says, matter makes gravity, gravity makes basins, flow lines slide downhill toward dense nodes. Simple enough. Enter the Great Attractor. Back in the 198s, a group of astronomers nicknamed the Seven Samurai noticed something off. Galaxies weren't just following Hubble expansion. They had extra motion, peculiar velocities, that seemed to point us toward the constellations Centaurus and Norma. Dressler and colleagues called the unseen mass in that direction the Great Attractor. It sounded like a monster cluster, but there was a catch: you could drive a galaxy through. The Zone of Avoidance. Our galaxy's disk is loaded with dust and gas. Along the plane, it blinds us in visible light and hides around 20% of the sky from standard optical surveys. So for decades, the very region where our flow seems to point was the region we literally couldn't see. If there was a giant mass there, we would have missed it. That shaped belief. It made hidden mass the default assumption. On paper, the fix seemed easy. Fill in the blind spot, add the mass, balance the books, because the books did not balance. Our local group's 600 km/s peculiar velocity is big. When astronomers tallied up known clusters and superclusters, the expected tug fell short. You could add Norma cluster, Centaurus, Hydra, and it still didn't quite explain the direction and the magnitude together. The map, built from light, kept disagreeing with the map built from motion. Here's the thing. Velocity reconstructions don't care about what you can see. They take galaxy distances and redshifts and infer how matter must be arranged to produce the observed flows. When teams pushed those methods, the flow lines didn't stop at the Great Attractor region. They kept going, pointing farther to a heavyweight called the Shapley concentration, hundreds of millions of light-years beyond. That helped because Shapley is real, massive, and not hidden by our dust, but it didn't fix everything. The directional shear nearby, the sideways stretch in local flows, still looked wrong if the full story was just big lump over there. So which map do you trust? The catalog of light with all its gaps, or the river of motion, which sees through those gaps indirectly? The stakes are not just academic. If we're wrong about what's steering us, we're wrong about the shape of our home basin. And if we're wrong about the basin, we're wrong about how the next few billion years of structure growth plays out. The future path of our galaxy depends on the slope of space in our neighborhood. This is where authority met reality. For a long time, atlases of clusters and superclusters gave us the frame. Names like Hydra, Centaurus, Norma, Vela. Meanwhile, the peculiar velocities kept whispering the same story. There's more going on than a single gravitational well. Every time someone tried to close the gap with more mass in the zone of avoidance, the numbers would budge, then stall. We could see pieces, thanks to infrared and radio peeking through dust, but the residual flow, what remained after you accounted for all that, stayed stubborn and directional. Think about that like reading a landscape by watching rain. You don't need to see the valley if you can track the streams. If the streams bend in ways you can't match to any visible ridge or gorge, maybe the ground isn't shaped the way your old contour lines say it is. Maybe the contour lines are wrong, or maybe the ground itself is doing something new. And this is the central question that takes over the story. Is the Great Attractor just mass we couldn't see because of dust, or is it a hole in our rules? A place where the way space expands and curves creates a gradient, a tilt, that guides motion without a single object anchoring it. Before we jump to that, we have to be fair. People tried everything practical within the standard playbook. They hunted for the missing light, They modeled biases. They adjusted selection functions. They extended the survey. The sensible path was, look harder through the dust, add up the actual stuff, and see if the map of reality snaps back into place. That is exactly where we go next. Because when the numbers wouldn't balance, the tools changed. X-ray, infrared, radio, methods that see through the zone of avoidance and sketch the terrain from motion, not just light. And when those came online, the picture of Laniakea and the thing we were calling the Great Attractor started to look less like a point and more like a slope. Inciting incident, the numbers would not balance. Here's where the story snaps. You take the local group's motion relative to the cosmic microwave background, about 600 kilometers per second, and you ask a simple thing. Does the gravity we've counted add up to that? Early on, the answer looked like yes if. Yes if there's a giant mass hidden behind the Milky Way's dust. Yes if we've undercounted clusters. Yes if selection bias is quietly tilting our catalogs. But when teams ran the actual sums, the ledger wouldn't close. People threw every sensible fix at it. Hidden clusters. X-ray surveys like ROSAT and the CIZA project started pinning down hot, massive clusters right through the zone of avoidance. They lit up the Norma cluster and friends in hard-to-see directions. Infrared catalogs like 2MASS plus radio HI surveys filled in galaxy counts where optical failed. The mass budget climbed. The direction sharpened. And still, when you plug those numbers into a velocity field, you don't get the full 600, and you don't get the right shear, the sideways stretch we see nearby. So the reconstruction folks took a different tack. Don't start from light, start from motion. Use distances, redshifts, and peculiar velocities to back out the gravity field that would cause them. That's what cosmic flow-style analyses do. When those maps matured, something jumped out. The flow lines pushed past the old Great Attractor region into the background, toward the Shapley concentration, a truly hefty supercluster complex hundreds of millions of light-years beyond Hydra Centaurus. That felt like a clean answer. Big mass far away doing the heavy lifting. Except it didn't fix the near-field geometry. If Shapley is the full story, local galaxies should lean a certain way. The measured shear field didn't quite match. There was a strong, coherent inflow in our neighborhood that lacked a single, sharp mass peak where the lines converged. You could tune the model with Norma and Centaurus and Hydra, and the vector still tilted wrong by tens of degrees. That's not a rounding error. That's a sign your picture is missing a piece. Around this time, another twist arrived. The push-pull idea. Density pulls, but emptiness pushes. When you're mapping flows, voids matter. A feature called the Dipole Repeller popped out of velocity-based maps as a large underdensity roughly opposite Shapley. It acts like a low-pressure zone in fluid flow, nudging us away while Shapley draws us in. That combination explains broad strokes, why we're moving fast, and why the CMB dipole points the way it does. But even adding the repeller to the ledger, the local drain signature stayed too strong for the counted masses. So the inciting incident isn't a single paper or a single discovery. It's the creeping realization that every time you add real mass into the blind spot, the residual flow refuses to die. X-ray says more clusters are there. Infrared confirms more galaxies. Radio fills in gas-rich systems behind the dust. Good. The budget looks better. Yet you subtract all of that from the velocity field and there's still a net convergence in a corridor, not a clean point. The numbers move, but they won't balance. This is also where kinematic breadcrumbs show up. The kinematic Sunnyeve, Zel'dovich effect lets you weigh bulk motion by how moving galaxy clusters tweak the CMB. Stack enough clusters, align them with the suspected flow, and you sense a common drift. Those stacks hint at coherent motion along the same axis where the gravitational map acts like a sink, strengthening the case that the flow is real, not just a catalog bias. Meanwhile, the CMB dipole alignment with our local flow keeps looking a little too tidy, like two anchors lining up on the same rope. And then there's the zone of avoidance itself. It was always the easy villain, but once CIZA and 2MASS reduced that blindness, we lost the excuse. If a hidden monster halo was sitting there, weak lensing and X-ray temperatures should start to betray it. They don't, at least not at the amplitude needed. What we do see is a ridge-like structure, a tilted terrain that keeps guiding motion even when you've added up the obvious lumps. So the incident is simple. You hold mass on one side of the scale and motion on the other, and you wait for equilibrium. It never lands, which forces the question that kicks us into the next act. If not a single anchor, what field, what slope, what shape of space can create a drain without a drain plug? X-ray vision through the zone of avoidance. So we aim the right eyes at the dark. X-rays first. Hot gas in galaxy clusters shines in X-rays even when dust blocks starlight. ROSAT laid groundwork, then the CIZA project went straight through the Milky Way's plane and started flagging clusters the optical sky simply missed. Get this, the Norma cluster lit up like a furnace. Others too, strung along Hydra, Centaurus, and deeper. The easy story should land here. You found the mass, now the flow lines calm down, right? Hold on. The vectors barely flinched. Infrared stepped in. Two mass mapped the whole sky in near IR, where dust bites less. Suddenly the zone of avoidance wasn't a blank wall, it was a dim window. Behind it, galaxy counts swelled, filaments showed up, and the outlines of supercluster walls matched the directions people inferred from motion. Radio followed. HI surveys, using the 21-centimeter line, pulled gas-rich galaxies out of the haze, especially low-surface brightness ones that optical surveys undercount. Piece by piece, the blind spot filled. Yet the residual stayed. When teams took those new catalogs and built mass models, the net flow didn't collapse into a single center the way a hidden black hole would force it to. Instead, reconstructions from peculiar velocities, cosmic flow-style maps kept sketching something like a ridge, not a dot. Imagine a tilted spine cutting across the region with streamlines curving along it rather than diving to a point. That shape matters. In a point-dominated pool, divergence maps show a sharp sink. Here, the divergence looked smeared, extended, almost like a valley floor bending you sideways. Planck and other microwave data added a different lens. The kinematic Sunny Zel'dovich effect lets moving clusters imprint tiny temperature shifts on the CMB. You can't read one cluster cleanly, but stack many along a suspected flow and you get a whisper that turns into a murmur. Those stacks lined up with the same axis, the same corridor the velocity field called out. Different instrument, different physics, same direction. That's a red flag for not a catalog artifact. Meanwhile, X-ray temperatures and luminosities gave us ballpark masses for the newly found clusters. Big, yes. Monster enough to own a 600 km/s motion by themselves. No. If a single hidden halo were there, something like a dark god under the dust, weak lensing should also hint at it by distorting background galaxies. Even in hard directions, the constraints we do have argue against a one-thing solution. The terrain looks busy and heavy, but not singular. Here's where the metaphor shifts. We stop asking, where is the object? And start asking, how is the ground shaped? Build the gravity field from motion, not light. That means solving for a potential that best explains a whole set of distances and redshifts, then cross-checking with what we actually see in X-ray, IR, and radio. When you do that, the basin boundary of Laniakea gets sharper and something else snaps into place. Flows bend because the slope tilts. If the slope tilts, you expect arcs, not straight plunges. That's exactly what the maps show through the once hidden zone. And the zone of avoidance excuse. It shrank. CIZA put pins on hot clusters. Two mass and HI filled the galaxy catalog. Selection biases were modeled and beaten down. The residual, the part that refuses to vanish, sits along a dark corridor that angles past Hydra, Centaurus toward the background heavyweights, but it keeps its own identity. It behaves like a guide rail shaping motion more than a single anchor pulling it. So what are we really looking at? One reading says it's just the sum of many hands. Norma, Centaurus, Hydra, Vela plus Shapley pulling from the back plus voids lifting from behind. Add enough vectors and you get a corridor. But the shear is too clean, too coherent for that to be the whole thing. The velocity-derived field points to an extended gradient, space itself sloping there, stronger than the light alone predicts. That's the pivot. When you can see through the dust and the flow still curves into a lane with no crown jewel at the end, you stop hunting monsters. You start tracing the ridge. And if terrain is the story, then tilts matter more than peaks. Which raises the next hard question. What could tilt the terrain without piling up a mountain of mass? The basin and the drain. So let's treat Laniakea like a real watershed. Not metaphor, a working map. Draw streamlines from peculiar velocities. Where lines converge, that's down. Where they split, that's a divide. When researchers traced those lines, a boundary snapped into view. On one side, flows feed Virgo and our local group. On the far side, streams peel away toward Perseus, Pisces, and beyond. The surprising part is that there's a boundary. It's that the lines don't dive into a neat bullseye. They arc. They lean along a corridor that looks more like a tilted valley floor than a pit. Here's the thing about basins in gravity maps. You can have a deep spot because there's a heavy object, or you can have an extended slope because the potential changes over distance without a single spike. The first gives you a node. The second gives you a ridge or a trough. The flow reconstructions through Hydra, Centaurus into the background keep favoring the second shape. It's like someone set a long plank under the cosmic web and lifted one end a few millimeters. Subtle, but over hundreds of millions of light years, subtle wins. Weight, gravity is push and pull, right? We don't live in a world where only overdensities matter. Underdensities steer you too. If a void grows, the matter around it moves away. That's the repeller idea baked into velocity-derived maps. When teams backed out the field from motion, a large underdensity showed up roughly opposite the Shapley side. They called it the Dipole Repeller, not because it pushes like a hand, but because the absence of mass there lowers the potential, so the gradient points away. Combine that with Shapley's pull and you get a dipole, drawn forward, eased from behind. Here's where it gets interesting. Even with that push-pull in place, the streamlines don't resolve to one anchor. They bend into a dark corridor. Picture a highway ramp that guides cars gently, even if the city center isn't there yet. The ramp shows up in divergence and shear fields as an extended region of net inflow, not a sharp sink. That's odd if you're counting on a single crown cluster. It's less odd if the basin itself is shaped by something more global, curvature that varies with position, or a small gradient in the local expansion. Hold on, expansion. The standard picture says on very large scales, space expands the same in every direction. Locally, gravity makes lumps, but if there's a mid-scale gradient, meaning expansion is a hair slower along one axis than another, you'd feel a steady drift even without a monster mass. That would show up as a tilt in the effective potential. Your clock and ruler would still pass local tests. Yet over tens of megaparsecs, flows would arc the way water hugs a curb. That's the drain behavior without the drain plug. Now the stakes jump here. If the slope comes from curvature or expansion changes, then cosmic time isn't identical everywhere on these scales. Not by a lot, but enough that two observers separated along the corridor could measure slightly different Hubble flows. Stack those small skews across a supercluster, and your velocity field remembers it. That can look like momentum vanishing into a sink, when in fact momentum is fine and the metric under it is uneven. So how do you separate a mass corridor from a metric tilt? You check consistency across probes. X-ray temperatures give masses for clusters. They don't sum to a point source. Weak lensing, where we have it, doesn't whisper of a hidden leviathan. Infrared and HI catalogs show filaments, yes, but no single colossus. Meanwhile, velocity reconstructions keep screaming ridge. And the kinematic Sunny-Eve, Zel'dovich stacks which don't care about starlight hint at bulk flow aligned with that same lane. Different windows, same slope. There's another test baked into the basin view. Watersheds meet at saddles, not peaks. In the flow maps, the Laniakea boundary touches other basins at elongated saddles, not tidy points. That's classic for an extended gradient. If a one-thing attractor rule, divides would pinwheel around it. Instead, the divides look like seams, long and slightly curved, separating streams that slide along, not fall in. That is drain-like guidance. You feel a steady pull sideways to the ridge rather than a plunge. And yes, voids matter. The dipole repeller isn't a footnote. Remove it from the model and the broad direction and speed wobble. Put it back and the vector steadies. But the repeller alone can't square the near-field shear. Its geometry sits a little off the lane that the flows prefer. So we end up with a hybrid picture. Density ahead, under-density behind, but also a shaped middle, a tilted trough that strings the influences together. So what carved that trough? If you're strict, the safe answer is the summed gravity of many structures. Norma, Centaurus, Hydra, Vela, Shapley. Add their halos, connect their filaments, stir in the voids, you get an extended potential. Fair. But the amplitude and coherence of the shear suggest there's still slack between light and slope. That slack is the opening. Maybe the metric in this patch is slightly creased. Maybe expansion isn't perfectly isotropic at these scales. Either way, the basin looks real, and the drain looks like a property, not a plug.